Example 4-3 is about a uniform flow in trapezoidal channel. So a 5-meter wide trapezoidal channel with the side wall angle of 1 vertical to 1.5 horizontal is laid on a slope of 0.00035. The Manning's roughness coefficient of the channel bed and walls is the 0.015. So we are asked to calculate the normal depth for a discharge of 20 cubic meter per second, the corresponding Froude number, and the slope at which the critical depth is equal to the normal depth, which is called the critical slope. So here we have the sketch of the channel, 5-meter width, a slope of 1 vertical to 1.5 horizontal, and then we have the Manning's coefficient, longitudinal slope and discharge. So we use Manning's equation. For trapezoidal channel, we have area as B0 plus MYN times YN, and the hydraulic radius is area divided by wetted parameter. So when you insert the values of the channel bed and sidewall slope, Manning's coefficient and longitudinal slope, then in the left-hand side, you have the discharge, and in the right-hand side, you have one equation, which is only related to the normal depth. So we go to the Excel file to share the Excel file. Okay. Good. Okay, so here we have developed Manning's equation in Excel. So here I have 5-meter width, 1.5 times YN. So I select one of the cells as YN, divide by Manning coefficient, and then area, divide by hydraulic radius to the power of 2/3 times the longitudinal slope to the power of 1/2. So here I start with 1. So given discharge is 20, and then this is the calculated discharge. So calculated discharge. So for 1 meter, it gives me a discharge of 6.7. Then I select 2. So it's the normal depth should be between 1 and 2, or close to 2. So maybe 1.7. So maybe more, 1.8. Very close, 1.81. Very close, 1.82. So you see that the normal depth is 1.82 meter. Part 2 asks to calculate Froude number. So Froude square in general formula is discharge to the power of 2 plus the top width, which is the bottom width plus 2 times of depth times sidewall slope, divided by GA to the power of 3. So I have 9.81 plus area, which is 5 times MY times Y to the power of 3. So it gives me Froude square equal to 0.15, and then I need to take the square root of that. So Froude number will be 0.39. And part C of the problem asks to calculate critical depth. So we know that the critical depths start when you have Froude number equal to 1. So here, if I put the value of normal depth, it gives me the value of Froude number here. So I can just simply copy this one here and then put the value of Y. And then I need to do try and error to get Froude square equal to 1. So if I put 1, is supercritical flow. So the depth should be slightly more, maybe 1.1. So it's slightly less, 1.05. So you'll see that the critical depth is 1.05 meter because it gives me a slope of very close to 1. So if I want to make this one even more accurate, I had to slightly reduce the critical depth, maybe 4.9. No. Maybe 5 is good enough, yes. 5.1, 5.2. 5.3, 5.4, yes. So would be 5.35. So you see that I can make that as accurate as possible. So this would be the accurate value. So you can just play around with the value of critical depths to make the fruit number exactly equal to 1. So the 3 digits after the decimal point or 2 digits for depths is enough. And then we need to calculate the discharge. So basically what I do is I write an equation based on YC, and then the only unknown is the slope. So now I can put the value of the slope, 0.334, for example. Now you see the slope is slightly larger than 20 cubic meter per second. So maybe 0.0003, maybe less, 0.0025, so maybe more, 26, less, so 258, 257. Yes, so this would be the critical slope. So we show that with S sub C. So this is how we can calculate the critical slope and critical depth.